the other day. So we had worked a problem like this. We had been working with buffers. If you've got starting concentrations, then what's the pH of that buffer? And then if you've got a buffer and you've added some acid or base to it, that's going to first use some sodium geometry. And then you actually produce a new buffer, but it's close to the ratios of what the old buffer was. So the pH is going to be close to what the old buffer was. But we did some calculations of how to figure out what the pH is going to be now that we've added a little bit of acid or whatever the situation requires. Then the last idea, connected specifically to buffers, is this one here. That's the last thing that we looked at. Was the other side of the buffer is what if I want to make a buffer of a specific pH? How much acid and how much conjugate base component should I put together in there? Because again, a 1-to-1 equal ratio forces the pH to be whatever the pKa of that acid is. But I can go up or down by 1 pH unit reasonably so. So if I modify the ratios a little bit, that's where I get that new pH. If I push it too far though, then I've exceeded the capacity or the range of the buffer, and then I've got to switch to some different substance to try to make a buffer. But a question like this we worked out, so ratio of sodium formate to formic acid for a pH 4.25 buffer, knowing the pKa of formic acid is 3.74. So all we do is just stick that into the Henderson-Hasselbalch equation, and we're looking for that ratio of the conjugate base to the conjugate acid. And in this specific example, we came out with a ratio of 3.24, which means there's really a range of actual concentrations you can use. Just make sure that your conjugate base is about 3 1/4 times as much as what your acid is. And that's really what that ratio of 3.24 means. So just make sure that you've got 3.24 times as much conjugate base as you can form. The simplest thing would be to simply do a 3.24 molar conjugate base and a 1 molar formic acid, all in one solution. Those are kind of high concentrations, and sometimes you can't get that much to dissolve. Because there are solubility limits to salts. Although sodium salts are soluble, there's always still a limit to just how much you can get. It's a high limit, but there's always still a limit. So in practice, we probably put a 0.3 molar and a 0.1 molar kind of thing. I think that's what I mentioned the other day. And so then I left this problem for you to practice. Hopefully, you do that. Just to kind of keep yourself fresh when working on it. So if I want a 3.75 buffer and I've chosen benzoic acid to make that buffer whose pKa is 4.19, then what you should have found from this, using the same methodology, is that in this case we need a 0.36 to 1 ratio. So not a 3 to 1, but a 0.3 to 1. So this actually means I need more of the acid than I do of the conjugate base. So 0.3 times as much base, conjugate base, as acid, which means more acid because that number is less than 1. And then the very last thing that we did actually talk about was capacity. There is a limit, but here are the general principles. There's a nice one simple slide that kind of brings you back to the general principles about capacity. You'll get the greatest capacity for a buffer by being as close to equal amounts of acid and conjugate base as possible. Now, if you're focused on a particular pH, you don't have as much control over that ratio. But 1-to-1 ratio is best, and in general, the higher the concentration you can be, the better. And these last two bullets, as I mentioned the other day, if you know that your buffer is going to encounter acid conditions, that you can actually take advantage of that and choose a buffer system that's going to be better able to buffer acid than basic. Or if you know that it's more likely to be a basic push on it, then you can choose a buffer that's better about buffering against base as opposed to acid. So those equal numbers, even amounts, they're going to be equally good at buffering against acid and base. But when you start pushing in one direction or the other, you're going to be better at buffering one thing than you are the other. Any questions about those kinds of things so far? So So really that concludes our buffers, the specific analysis of buffers for the setting. What we're going to do next is titrations, which is more in line with what you guys were doing in lab the other day. What we're going to do is we're going to break a titration down into its individual parts. And one of those parts is a buffer. One of those parts is going to be the solution of a salt. One of those parts is going to be where you have excess acid or base, depending on the nature of your titration. And then one of those parts, at the very beginning, is just a pure solution of either your weak acid or your weak base. So there's actually 1, 2, 3, 4 different sections of a titration. Each one has its own analysis that has to be done. That's what we're doing. So questions about the buffer stuff before? On this Friday morning. Sometimes it comes up. When we're ancient Greek, we have our trail, grass, and tar. I don't know how much they learned, but that's it. So a titration. There's some words here. You just need to be a no. So burette, we didn't use a burette. Burette's just a specialized piece of equipment that a lot of general chemistry labs will tend to use, but it takes a large volume of stuff, so we don't do it. There is also an indicator, so we work with those as well. You know that there are these plant pigments that can change color. Be one color under acidic conditions and another color under basic conditions. So that's what the indicator is. It's just something that can change color when the pH changes. So we did for several different of those. And then we had that universal indicator that was actually a mixture of some 5 or 6 separate distinct indicators. There's two words here, the equivalence point and the end point, which are not the same, but they're similar, they're close words to each other. Start with the equivalence point, the last one down there at the bottom side. The equivalence point, as the name implies, is where you have equivalent moles of acid and base. So at some point in the titration, you are at that special spot where complete neutralization has occurred. The stoichiometry is just right, and you have just as many moles of acid as you do base in the solution, and so you have perfect neutralization, which means at that particular moment there is no more acid, there is no more base. There is only a pure salt solution. Now that salt may be the salt of a weak acid, so it may have its own equilibrium on the bottom. If you started with an acid and a base, at the equivalence point you have put in exactly equal amounts mole-wise, not molarity-wise, mole-wise of acid and base. So you've completely neutralized the acid and the base. The end point, on the other hand, the end point is really a product of my indicator. Those indicators, right, are two different colors. One in acid solution and one in base solution. So when you start your titration, that indicator is a particular color. And when the pH switches to whatever the pKa point of that indicator is, the indicator switches color. When that color switch happens, that's the end of the point. Because when we're doing a titration, we're following a color change. And when that color changes, as far as we're concerned, we've reached the end. We've reached the equivalent point. The reality is we may or may not get the equivalent point. The equivalent point is a very well-defined specific location. It is when you have exactly equal amounts of acid and base in that solution. The end point is when the color changes. What we want to do is to choose an indicator. You saw that table from your lab book that had all these choices. You worked with 4 different indicators that were changing at different pHs. What we want is for that end point, when the color switch happens, to also be where the equivalent point is. We need to choose an indicator, and that's one of those questions we were asking in that lab was, what indicator should I use for this particular titration? And that was the basis of it. The basis is I want the endpoint, the color change, to happen right when that equivalence point is. Now the good news is the pH is really moving rapidly. You saw that on your graph. So at that equivalence point, the pH changes quick. And so we often have a nice range over which that pH is changing. So as long as my indicator is changing somewhere in that range, I'm good. What I don't want is to take an indicator who's going to change color before I ever get to the equivalence point, or who's not going to change color until I'm way past the equivalence point. That would not be a good choice. And we'll talk about some of those things as we go through titrations. So here's the burette thing. You got a flask. Again, what we did is we have drops of this and drops of that. So we don't need flasks. We don't need tens or even hundreds of milliliters. We just need 1 or 2 milliliters for our titrations. But the same principles hold for drop-by-drop business as it does for this big equipment. Much less expensive. There's all kinds of things that have caused me to use the equipment that you used the other day. The principles are still the same. The principles of chemistry are no different because you guys are using droppers and plastic as opposed to big long glass tube burettes and large flasks. There's nothing that you're going to gain extra from those kinds of equipment. So, titration curve. Again, that's what you guys are working with. You drew your own, you work through those. Just to plot a pH. There's an inflection point. That's at the equivalence point. That's where the curve changes direction, jumps. And then there's another inflection point on the other end of that. Well, technically there's one if it's strong acid, strong base. That's where that curve changes direction. The equivalence point, at that point, like I said, you have completely neutralized acid and base. And so what you have at that point is a salt. A salt that's a combination of the choice of acid and base that we're using in the titration. That equivalence point, pH, can be one of 3 places. It can be at 7, so it can be neutral. It can be a basic salt, so the pH is going to be above 7, or it can be an acidic salt, pH can be below 7. So we've encountered how to determine pH of salts before. So we'll have to keep that in mind as we work through this titration curve. Once you pass that equivalence point, though, the acid is completely gone. And once you pass that equivalence point, then the additional base that you continue to add is now in control. And it's really just a matter of figuring out how much extra base is present. Because the concentration of that base, heading to POH, is going to set the pH. So that's what happens after the equivalence point. So these are the things that we'll take a look at. So the first one, for a strong acid and a strong base, what you have in this case is the pure acid is first off in the container. And so the first thing you have, the initial pH, is just the pH of the pure starting acid. And because it's a strong acid, that's pretty straightforward. If it's 0.1 molar, and we know for a strong acid, that's 10 to the minus 1, that's the pH of 1. If it's 0.01 molar, then it's 10 to the minus 2, so that's the pH of 2. If it's 0.015, then we still just take the negative log of that, and we know what the starting pH is. For strong acid, whatever the acid concentration is, that's the hydronium ion concentration. What happens next, and you guys did this titration, what happens next is simply a matter of, every time I put some acid in there, it's going to neutralize, every time I put some base in there, it's going to neutralize some of the acid. So if I start off with 0.2 molar acid, it's going to drop down to 0.18, down to 0.16, down to 0.14. And so when that concentration drops, the pH starts to decline, but it's still just a matter of negative log of the hydronium ion concentration. Now the thing is that there's some stoichiometry that tells me how much of the acid is still there. How much of the acid is now still there? How much of the acid is still there? How much of the acid is still there? Until eventually you get to the point where you've added just as much base as you have acid. And that's the equivalence point. And if this is a strong acid and a strong base, then what you are going to have is the cation from a strong base and the anion from a strong acid. And so that anion of a strong acid is a relatively weak the cation from that strong acid is typically a sodium or a potassium. Something here is a pH neutral. So the whole salt is going to be pH neutral. And so for a strong acid, strong base, that equivalence point is always at pH 7. So really for a strong acid and a strong base, there's nothing to calculate as far as equivalent point. Strong acid, strong base, pH 7. Nothing to calculate. In fact, I have nothing to actually calculate with. So I couldn't even do a calculation if I wanted to. But we know where it's going to be. It's going to be at pH 7. Once you get past that, all the acid is gone. No more acid. But you're going to keep putting in base. So I'm going to add some more hydroxide compound. And at that point, the only thing in there is that extra hydroxide. All the hydroxide I put in there up until then has been neutralized and it's gone. From that moment on, whatever extra hydroxide I put in there is what's going to turn into pH. If I had put in an extra, my solution at that point is now a 0.001, 0.001 molar hydroxide solution, because that's what the excess has done, is created a 0.001. And I know that the pOH is 3. Okay. So the pOH is 3, and the pH is how much, guys? The pOH is 3, how much is the pH? 11, yeah. So it's 14. The two together have to add 14. So pOH is 3, then pH is going to be 11. And if pOH is 2, then pH is going to be 12. So that's how I get to the pH of what happens after that. So typical titration curve for strong acid, strong base. And this just really talks you through the things that I just taught you. So let's do some math. All right, here we go. 25 milliliters of a 0.1 molar hydrochloric acid solution. That's what's in the container first. So I've got 25 milliliters, and that 25 milliliters is a 0.100 molar hydrochloric acid solution. Now, on that second line, they're telling us that the initial pH is warm. Do you agree? That 25 milliliters of a 0.1 molar hydrochloric acid solution that the pH is warm? Okay. See some. What if this was actually 50 milliliters? Of a 0.1 molar hydrochloric acid solution? What would the pH of that be? What? Still 1? Yes, still 1. Why? The volume doesn't matter. It's the concentration that always causes pH. Now we're going to need that volume soon enough to have to work with that volume to figure out some other things. But the concentration is really all that matters when we're trying to determine pH. Okay. Here's where my volume did come in. I'm going to start to add base to this. I'm going to need to know how much base I've added. And that base is going to be a certain concentration and a certain volume. There's going to be a certain number of moles of hydroxide in there. That's what I'm going to track. Because for every mole of hydroxide I add, I'm going to remove 1 mole of the acid, because that's what acid bases do. The acid and the base react to make a neutral salt and water. So every one of these I put in there is to take away one of those. So how many do I have to start with? And that's what this calculation is. Notice I've got to change from milliliters to liters because molarity, capital M, has those units of moles and liters. So this time, I have to change liters. So I know exactly what the moles are. And as it turns out, I run the calculation, and here's what I've done. So in these 25 milliliters of 0.1 molar hydrochloric acid, I start off with 2.5 times 10 minus 3 moles of HCl. So that's what I have. So what I want to do is I want to step in here and I want to add 5 milliliters of my 0.1 molar sodium hydroxide. So now I need to do some stoichiometry. 5 milliliters is what I added to get this 0.1 molar sodium hydroxide. So how many moles of sodium hydroxide did I add? Where'd I get this 0.005? Come up there somewhere. Where's it at? Okay, that's changing milliliters into liters. 0.005 liters. And then I multiply it by 0.1. What's that 0.1 from? Yeah, it's the concentration of the sodium hydroxide. Not the concentration of the hydrochloric acid, because that's not what I'm at. And as it turns out for this example, they started with equal concentration. In your lab, it was 5 to 1, right? You had a 0.01 molar hydroxide, you had a 0.05 molar hydrochloric acid. So I've got this many moles of sodium hydroxide, which means I have that many moles of hydroxide. The initial moles of hydrochloric acid. So 25 milliliters. And 0.1 molar. So that's where those two numbers are from. Yes. So what I got to do is put this into a stoichiometry problem. That's really what I'm getting at here, stoichiometry. So I want to know how much base I just added, and here's how much I added. I added 5 times 10 to the minus 4 moles. Now that base is going to get rid of that same amount of acid. So I'm going to get rid of 5 times 10 to the minus 4 moles of acid. I started with 2.5 times 10 to the minus 3. That base that I just added is going to use up this many moles. So that's going to use up that same 5. That's going to use up that same number of moles of acid. So if I subtract those two numbers, I'll find out how much acid I have left. That's what I'm trying to do. How much acid is left after I put some base in? That base is going to cancel out. Same kind of acid that you not base. So if I started with 2.50 times 10 to the minus 3, and I subtract off 5 times 10 to the minus 4, how much do I have left? If I did my math correctly, this is what I get. 2 times 10 to the minus 3. So, if I now have this much acid, number of moles of acid present, what you can do is simply take the negative log of that. That's not how it works. What I need is the hydronium ion concentration. That's the number of moles. How do I get from that back to concentration so I can take the negative log? is the molarity. And what is the molarity? If I have 2 times 10 to the third moles. I know there's one step over there, 2 times 10 to the third, but it's not. So what do I need to do? That's the number of moles. Okay, it's got to change the liters, but yeah, and good to recognize that now my volume is 30. See that now the volume is 30. Started at 25, and I added 5 milliliters of hydroxide, so now I'm up to 30 milliliters total volume. So 2.00 times 10 to the minus 3 divided by 0.030, that's 30 milliliters in the liter form. I divide those two. 2 times 10 to the minus 3 divided by 0.03. That number. Oh, okay. So the molarity is 0.067. So what's the pH? Negative over that. pH. 1.2, 1.18, depending on how and where you round it. So the pH of this is 1.18. Initially it was at 1, and when I added those 5 milliliters, it's going to go up by 0.18. Oh, what we're actually doing is we're just working our way through the titration curve. So what we're going to do is we're going to find some points. And I'd like to say you just did it. You put in 1 drop of acid, and you put in 1 drop of base to a different concentration. You just looked to see what color it was and compared it to your color strip to determine what the pH is. And I told you that that curve was computer generated. This is the exact calculation the computer could do to make that curve. What you're doing is calculating what the pH should be because of the stoichiometry. So I take my liters of added sodium hydroxide, the concentration of that, I determine the number of moles of sodium hydroxide. That number is 5 times 10 to the minus 4. Now that I have that number of moles of hydroxide, I know that that number of moles of hydroxide is going to consume, if you like to take that's fine. That number of moles of hydroxide is going to consume the same number of moles of acid, because it's a neutralization reaction. It's not an equilibrium, it's going to happen. That's going to get rid of all the hydroxide that I just added. It is going to form sodium chloride, but I'm not really concerned about that. But if you want to track it, you can. But here's the important part, is if I start with this much acid, and the hydroxide is going to consume this much acid, this is what I have left. But pH is a concentration thing, so I don't just use the number of moles, I've got to get that back into concentration. So I need to recognize that if I started at 25 and I added 5, and now I'm up to 30, which is 0.030 liters. So my new concentration is 0.0667, and the pH of that, so the pH of that is 0.1. So I started at pH of 1 with just 125 milliliters of 0.1 molar hydrochloric acid. I added 5 milliliters of 0.1 molar of sodium hydroxide. It neutralized the equivalent amount of whatever that moles was. And then what I had left is now in a new volume, and boom, this is my concentration. And that, therefore, is my pH. What I could then do is say, okay, let's go in and let's add another 5 milliliters. What you would do is calculate how much is that. And then you would subtract that off into how much acid you had and see how much remains after that. Then you would take that number of moles and divide it by the new volume, which would now be 35. You would get a new hydrochloric acid concentration and a new pH. This concentration should be going down because I'm adding base and taking away hydrogen chloride. So that pH should be climbing up. And it's going to keep doing that. Add another 5, add another 5, until eventually I'm going to get to the equivalence point. And if I have 25 milliliters of 0.1 molar acid, and I'm adding 0.1 molar base, how many milliliters of base is it going to take to hit that equivalence point? 25 milliliters. Because the concentrations are the same. The volumes of added material will vary. Again, back in your lab, you just had 1 drop of acid. And it took 5 drops of base to get to the equivalence. Why did it take 5 times as much volume? Because the concentration is different. Specifically, we need 5 times less. That's why it took 5 times more. So of course, if those concentrations are different, then the number of milliliters required to get to equivalence will be different. And you guys will need to, that's actually the first thing I would do when I'm doing these calculations, is to see where that equivalence point is going to get. It's very important that you know that happens at 25. Because if you don't recognize that that happens at 25, and I say, what's the pH going to be when you've added 20 milliliters? Or if I say, what's the pH going to be when I add 35 milliliters? You won't really know what part of that curve you're in. Because the calculations are different depending on what part of that curve I'm in. Yes, ma'am?
So if the NaOH is 0.05.
Yeah, so if this NaOH was actually 0.05, then that would not be 25 milliliters. No. How much would that? Okay. It depends on this.
Well, if the HCl was the same. It just depends.
If the HCl was 0.1 and the base was 0.05, it's going to take twice as much as this. Because it's half the concentration. It's going to take twice as much. So this would take 50 milliliters to get to the equivalent. And what we did, what I was saying is what we did in lab is we used 0.01 here. Oh, sorry. We used 0.05 here and 0.01 here, which is why ours took 5 times as much. 1 drop to 5 grams. 10 milliliters, 50 milliliters. But yeah, those ratios determine where you're going to reach that equivalence. Yeah, so if it were 25 milliliters of 0.05, that would be 125 milliliters of 0.01. Yes. Exactly. Good. So we keep adding and we keep adding. We go back to our stoichiometry, go back, calculate, until we get to what we know is the equivalence point. At the equivalence point, because, as I said, this is a strong acid and a strong base. When I hit the equivalence point, there's no calculation to do. I know it's going to be pH 7. What I do need to know is when it's going to happen. So when I get to 25 milliliters of that added base, then I know I'm at equivalence point. No calculation to do with pH 7. Case closed. Because that's a neutral salt. Oh. And if you're wondering, there's a calculation, stoichiometry calculation. A lot of times you can kind of do these in your head, but if you want to see how that pattern works out, that's how you determine it. So again, at the equivalence point, nothing to do. I know that I've added 25 milliliters of sodium hydroxide. There's real no calculation because the number of moles of sodium hydroxide, the number of moles of the acid that I started with are the same. So at this point, there is no acid left. All my hydroxide that I've been adding all along is totally gone, and what I have left is nothing but a sodium chloride solution. So what I have is a solution of sodium chloride, and the concentration of that sodium chloride really does not matter because it's a neutral salt. It's salt with strong acid and strong base. After they put, so after I've added 25 milliliters, if I put in another 5 milliliters, so if I step in here and I've got myself all the way up to 30 milliliters of sodium hydroxide, how many of those milliliters did it take to get to equivalence? 25 of them. So the first 25 of those 30 have now erased all of the acid. What that means is that all that's left now is the hydroxide that's in those extra 5 milliliters. That's it. So back to my original calculation, how many moles is that? That's 3 times 10 to the minus 3 moles of hydroxide. Putting that into my table, here's what I notice is that 2.5 times 10 to the minus 3 is what it takes to neutralize the acid. So that wipes out the acid. Yes, it makes some salt, but again, for a strong acid, strong base, that salt doesn't matter. It's a neutral salt. But I need to now track, after the equivalence point, I need to track how much base is left. So I'm going to have 5 times 10 to the minus 4 moles of sodium hydroxide left. But I'm still asking about pH. Since I've got extra hydroxide, the quickest calculation I can do is pOH. The pOH means I need to know the OH concentration of the brackets. I need concentration. The concentration is not 5 times 10 to the minus 4. Concentration is 1. 30, on the right track. About 35. Come on. 55. Ah, that's 55. So it is 5 times 10 to the minus 4 divided by the 55 milliliters, because it's 30, plus the 25 that I started with. So I can't leave it as milliliters. I'm going to change it to meters. It's actually divided by 0.055. And 5 times 10 to the minus 4 divided by 0.055 is that number, 9.09 times 10 to the minus 3. I'm going to take the negative log of that and get 2.04. So the pH is 2.04. No. pH is not 2.04. What is 2.04? pOH. Yeah, you're right. I thought we were doing this. We were. So the pOH is 2.04. So if the pOH is 2.04, the pH is 11.96. If I add another 5 mils, 35 mils, then I still know that 25 milliliters of that is what was required to neutralize the acid. That means I have 10 milliliters of extra. And that's how many moles? I can calculate that. Take that number of moles divided by what the new volume is. Get the OH, take the negative log of it, get the pOH, and then I know what the pH is. So I have 0.0091, 0.00909, depending on how many six peaks you want to came up to.
You will have the bonus point, you'll have the pH, you might add more. Again, more.
Yeah, I think it's an easier thing for me to calculate. Because what I know is hydroxide concentration. when I have the hydroxide concentration. Before, what I want is to, I always want hydrogen concentration. That's usually the easier thing. When you get past the equivalence one, it's actually easier yet. Calculate the pH. You still always want pH. Because that's what my curve is based on. My curve is based on what's the pH with a certain amount of added hydroxide. Now again, in lab the other day, you guys had a pH here that you were actually measuring. Here we're calculating. And that's what the computer did to make that curve that you saw already on the page. And then your curve was similar. Okay, I know it was lab, it's here now. Your curve is similar in shape to this one. So here's what we've done so far. What's the very beginning pH when I haven't added any sodium hydroxide? That's just the chloric acid concentration. That's the only basis. And then what I do is I said, okay, if I added 5 milliliters, what's the pH? And it went up a little bit. We did not do the calculation where you add 10, 15, and 20, but you could have. You just go back through, see how many moles that is, subtract off the number of that from the number of moles of acid, whatever extra acid is left out of the total solution volume, then gives you pH. However, we did know that there is a special equivalence point at 25 milliliters. We know that's at 25 because we did the calculation to see that that's okay. And at pH, at the equivalence point, we know the pH is 7, and there's really nothing to calculate. Strong acid, strong base. You go past that, and then the hydroxide is the control, and what we just need to know is how much extra hydroxide have we now put in. The first 25 milliliters neutralize all of the acid, and the extra above that now leaves some excess hydroxide. So we just calculate 11.96 for 30 milliliters. We did not do that, but we could have gone on to 35 milliliters and calculated the next one. And what you would get is pH 12.22 if you did the calculation. You could then go on to 40 milliliters. pH is going up. It's not going up by a whole lot, 50 milliliters. So when you put in twice as much hydroxide as required, that 50 milliliters is twice the equivalent. Your pH is still not much higher than it was when you were only 5 milliliters. And that's just because you've got rather dilute solutions. But you could do those calculations. So, this is a titration curve. It has 3 areas. The starting spot, the excess acid until you hit the equivalence point. And so the equivalence point is the 3rd location. And then you've got the after the equivalence point. That's your 4th location. You've got the beginning, a rise where you have a little bit of extra acid left over, then you hit the equivalence point, and then you've got the acid beyond. Each of those has a different way to calculate what it is. That's what I need you guys to recognize. Different calculations for each part of it. One of them is actually not a calculation at all. And which one is that? First one's a calculation. The equivalence point. This one. That's not a calculation. Because I know it's 7 because it's strong acid. Question. I'm going to leave this one to you. strong base with a strong acid, so if I start with my base in my container and I add acid to it, it's essentially the reverse of what we saw. They're the same derivative. The difference is, in the beginning, I've got a base solution, and I calculate the pH of that base based on the hydroxide concentration. And once again, the starting, the initial pH does not matter what the volume is, it only matters what the concentration is. And it technically always only matters what concentration is. But there are sometimes easy or more difficult ways to get it from there. But it starts high. There's still an equivalence point. This is still a strong base and still a strong acid. So you know equivalence point is still going to be pH 7. The difference here in the beginning is I'm not trying to figure out how much acid I have left over. I have to figure out how much base I have left over to check the pH. Hit the equivalence point, pH 7, no question. After the equivalence point, now I don't have extra base like I had below. I've got extra acid, and I need to figure out how much extra acid. Because that extra acid is what determines what the pH is. Same kind of calculation. So the next titration we want to talk about is that titration of a weak acid with strong base. So what this does is modifies a couple of different locations. Okay, fine. It actually modifies 3 locations. 3 locations. The initial is going to require a slightly different calculation. It's going to require an ice calculation. The second section, where we're looking at excess acid, we're not in the form. Now we're in a buffer zone. We're going to have to do a buffer calculation. And then the equivalence point is not going to be set. Weak acid and a strong base, we know that that's going to form a salt, which pH is going to be above 7. At that point, we've got the salt solution. Calculate the pH. And then after that, it's back to salt. Meanwhile, let's take a break. We'll come back to this when we get back from our break. So take 10. We'll get back at that. All right, so stoichiometry calculations. And in those stoichiometry calculations, focus on particular values. That's the key here. At the very beginning, it's just a solution of a strong acid. Whatever the concentration is of that acid determines the initial pH. After that, stoichiometry, yes, you're focused on how much acid is still in it. When you get to the equivalence point, you need to know where that's at. So you'll know when you get there. When you get to the equivalence point, strong acid, strong base, pH 7, nothing to calculate. That's what it's going to. Once you get past the equivalence point, now you're not focused on that acid that you started with. Now you're focused on how much extra base is there. So that's the pattern to work your way through any particular part of that calculation. And then what I do when I encounter these kinds of problems, the first thing I need to know is where the equivalence point is. Once I know where the equivalence point is, then I can decide whether 25 milliliters is after the equivalence point, or before the equivalence point, or at the equivalence point. And that's the way the typical problem will come to you. What's the pH of a titration solution that starts with 35 milliliters of 0.3 molar hydrochloric acid, titrated with so many milliliters of a such and such potassium hydroxide solution. So first thing you do is figure out where the equivalence point is at, whether you're before or after it. If you're before it, find out how much acid is in it. If it's after it, find out how much extra hydroxide is in it. If it's at the equivalence point, that's a nice easy question to answer. Correct? Or if it's the initial pH, then you just look at the acid and it doesn't really matter about the base because there's nothing to put into it. Next kind of titration that you commonly encounter is when you don't have a strong acid and a strong base, but you have a weak acid with a strong base. What happens here is you have an initial pH, but it is not simply the concentration of the acid because that acid is not fully dissociated. It's only dissociated partially. So we need to know the Ka for that acid to be able to determine what the pH is. And again, we actually determine those pHs from the previous chapter. But it's the same kind of an idea as we do at work. Knowing the Ka, knowing the initial concentration, you use an ice diagram and you solve for X, and the negative log of that X, which is going to be the hydronium ion concentration, negative log of that is going to be pH. Or if you recall the shortcut, as long as X is small, then the pH is going to be the negative log of the square root of the Ka times the initial concentration. That's the shortcut. Negative log of the square root of Ka times initial acid concentration. If you go through an ice diagram, that's a calculation you're going to end up doing. That's where you're going to end up. So if you like shortcuts, you want to memorize that sort of thing, you're welcome to. Because it's a nice, quick, simple, easy way to get to what you want. Because underneath there, that square root of Ka times Ha naught, you're getting concentration. That's the value for X. X is typically the hydrogen. But it's based on the Ka. And don't forget that Ka and Ha naught, those two are the ones that we're checking that have to be at least 10 to the third. So the starting concentration has to be greater than Ka by at least 1,000 times, or the X is small is not appropriate. And then you've got to go back and do a quadratic. Now the second thing that happens when you have excess acid, that excess acid is actually a weak acid and its conjugate base from the neutralization process. So at that point, right past the initial, all the way up to the equivalence point, you actually have a buffer. And if you have a buffer, what I do is nice, short, simple Henderson-Hasselbalch. Okay? But the concentrations you must know. And those concentrations are a result of stoichiometry calculation. kind of what we were doing back when we were talking about buffers in the first place. I have a buffer, and I add some acid or base to it, what's the pH? Well, first I have to figure out what the equilibrium, initial concentrations are, and then what the equilibrium are. So Henderson also buffed, because that's what we're at, buffer point. At the equivalence point, it's not going to be 7, because this is weak. One of the components is weak. So when you have a weak acid and or a weak base that you're titrating each other, then you're not going to be a neutral salt. But at the equivalence point, you have a salt solution. What you then have to figure out is what's the concentration of that salt solution. Because we have also, in the previous chapter, learned how to calculate the pH of salt solution. And of course, somehow it's going to connect to the Kb, because that's all that's in there is the conjugate base of that initial weak acid. After the equivalence point, then you're right back to what we were doing on the first one. After the equivalence point, because the equilibrium of that salt, because the equilibrium is no longer above the solution, because the equilibrium of that salt is really a small contributor, it's simply excess hydroxide. So whether it's a strong acid, strong base, or whether it's a weak acid, after the equivalence point, the calculation is how much extra hydroxide. It's just before that things are different. And in this case, the initial pH is different because it's a weak acid. But we've done those calculations. The equivalence point is not 7. It's the equivalence point of the salt solution, but we've done those calculations. Between those two, the initial and the equivalence point, is a buffer. And Henderson also buffer would be my choice of how to calculate that. You can use an ice diagram, or then go back to whatever you guys are comfortable with. But still, there's 4 zones. There's an initial pH, there's the buffer zone pH, there's the equivalence point pH, and then there is the active pH. So, let's see here. 25 milliliters, 0.1 molar formic acid, titrated with 0.1 molar sodium hydroxide. Initial pH. Help me. How do I calculate this? Okay. So if I'm doing the nice diagram, there must be an equilibrium reaction that I need to track. So what does that equilibrium reaction? What are the chemicals? What are the components? The what? There is an H3O in there somewhere. So it's going to be the acid plus water. And the conjugate base, CHO2 minus plus H3O. So there's the equilibrium. Spread my table over a little bit because I need to track 3 things. I need to track the formic acid, the formate ion, and the hydronium ion. The water is a pure liquid, so it's not a part of the equilibrium. So, I stands for, and what number goes there? Okay. Initial concentration of the formic acid is how much? 1100. Initial concentration of the formate, 0. Initial concentration of hydronium, 0. So when I was back doing weak acids, that's what they always started at. Whatever the weak acid concentration was, the other two guys would use. Now we're going to let the equilibrium do its thing. So the change in formic acid is going to be X, plus or minus. Okay. It's going to go down. And that's only because these two have to go up. They have no choice. So that equilibrium, that's going to be that, and this one's going to be 0.100 minus X. What's next? Okay. I'm going to do my expectation that X is small, so I'm going to kick that back to that. So what is the Ka? In there? 1.8 times 10 to the minus 4. Okay. Okay, so I know what K is. How do I use it? So X squared is equal to 1.8 times 10 to the minus 5. Here's my math, right? Multiply both sides by 0.1, so 1.8 times 10 to the minus 4 should become 1.8 times 10 to the minus 5. Square root of that. So the pH is negative log of that. .37. This is part where you said you could use it. Yeah, sure. My shortcut, if you remember, was negative log of square root of Ka times HA naught, which means negative log of the square root of 1.8 times 10 to the minus 4 times 0.1, which if you look at the math here, that's exactly what we did. So yes, this is where that shortcut like such. Keep track of it. And that's what you get. So yes, this requires a nice diagram. This is something that we have done. Maybe been a little bit since we have done it, but we have. If you want to check, you're at 4%. That's less than 5%. Fine. So I can live with that. And I can really see that already because that was 10 to the minus 4. This was 10 to the minus 1. I was right at that 10 to the minus 3 business. So 2.37. That's my initial pH. Now let's start adding some base. Wait, before I start adding some base, how much base do I need to add to reach that volume-wise? I mean, 25. Good. Okay, so that's always in the back of my mind. When I get to 25, I'm going to be at the equivalence point. So let's start by adding 5 milliliters. Same math that we did earlier because this is still a 0.1 molar sodium hydroxide solution. So that means I have added 5 times 10 to the minus 4 moles of sodium hydroxide. that 5 times 10 to the minus 4 moles of sodium hydroxide is going to use up that many moles of HA. And what use up in this case means it's going to convert it into its conjugate base. So at the beginning here, we didn't have any conjugate base. I put in some hydroxide, it got all used up. That number of moles is going to take off of that acid. Leave me with only this many, but it's going to change that acid into the conjugate base. So however many moles of base I add, the number of moles of conjugate base I'm going to end up with. So until I get to the equivalence. At the equivalence point, I can do a calculation there to see that all of that HA will be gone and nothing but the A minus will be present. That A minus is then going to connect into what pH is at that point. So, after I added my 5 milliliters, I've got 2 times 10 to the minus 3 moles of HA I've got left, and I have now produced 5 times 10 to the minus 4 moles of hydroxide of the conjugate base. I am still, I'm in a buffer situation now. So what I'm going to do is I'm going to use the Henderson-Hasselbalch equation, which says pH is equal to pKa plus the log of the base form over the acid form. The Ka, I believe, is 1.8 times 10 to the minus 4. Is that right? So what is the pKa? Log that. Negative log of 1.8 times 10 to the minus 4. 3.74. So that's going to plug in right there. Conjugate base, that's the number of moles of the formate. 2 times 10 to the minus 3, that's the number of moles of acid that's left after that first stoichiometry takes place. The base has been totally consumed, so there's no base left. The base that I put in is hydroxide. But what it's going to do is make the same amount of the conjugate. And so 5 times 10 to the minus 4, that's how much conjugate base got produced. 2 times 10 to the minus 3, 2 times 10 to the minus 3, that's how much acid is left. So 3.74 plus the log of that 2 divided by 7. And at this point, the pH should be 3.14. Stop here and let you tell me what the pH is going to be after I've added 15 milliliters of sodium hydroxide. Just kind of grab them. So we added 15 milliliters. Alright, so let's see here. 15 mils, 0.015 liters times 0.1 moles per liter is 1.5 times 10 to the minus 3. So that's the number of moles of hydroxide. That is going to subtract off of my original. So originally I had 2.50 times 10 to the minus 3. Now I'm going to subtract off 1.50 times 10 to the minus 3. Those are both 10 to the minus 3s. So it's just 2.5 minus 1.5, which is 1.00. So this is how much acid I have left. And this is also how much base, conjugate base, gets produced. Whatever strong base you put in there is the amount of conjugate base that gets produced. pH is pKa plus the log base over acid. pKa is still 3.74 because it's still the same system. Log base is 1.5 times 10 to the minus 3. 1 times 10 to the minus 3. That's really the log of 1.5. 0.5. Of 3.92, 3.916, but I'm around at 3.92. Awesome. So you could do the same thing for 10 mils, you could do the same thing for 20 mils, but 25 mils is a special location. 25 mils. 25 mils is the equivalence point. And you really have to know that that's where you're at, the equivalence point. When you reach the equivalence point, you have now added sodium hydroxide and the acid, and so now you have neutralized. There's no more acid left. You don't have any extra base in there. So what you have at this moment is simply a solution of that salt. But when it comes to calculating the pH of a salt solution, then I have to know what the concentration of that salt solution is. So now I'm back to where I do have to know the concentration. By the way, notice you weren't even using concentration for that chemistry block. You were using the actual number of moles. You could go back and change them into concentration like we had always been using the chemistry block. But the beauty of the math there is that the concentration ratio is the same as the mole ratio. So mathematically, you can save yourself some time. All right, so back to this. I've added equal amounts, so there's no more acid left. There is none. That base has also been totally neutralized by the acid. So all that remains is a certain number of moles of the conjugate base, the salt. And again, the sodium part of this doesn't matter because sodium is a neutral half. If this was an aluminum formate, that would be a whole different issue and much more complicated just because of that. So we won't deal with that. But that's what I have, just the conjugate base now. So I've got a solution of a conjugate base. And the number of moles of that conjugate base is the same as the number of moles of hydroxide, just like it always is. Whatever amount of hydroxide I've added, that's the amount of conjugate base that I've formed. So now what I have is simply the solution of a conjugate base. Let me give myself a little space. Here we go. So how do I solve that kind of problem? What is the pH of the salt solution? What does that equilibrium look like? what acid do I have? Okay, I have neutralized this. There's none of this left. So all I have here is the CHO2. It's a sodium salt, but remember the sodium part of that's a spectator ion. So all I'm interested in is this. Plus water, it's always plus water on the left. So what do I have on the right? That's what I have. So that's my equilibrium for that salt. And lo and behold, that CHO2 shows back up again. But this CHO2 is not the ones that we started with. This is the one that's produced from the equilibrium of the salt itself. Which those are K values and they're relatively small and there's not very much of it. Now we're going to have to figure out how much it is, because that's how you solve these kinds of problems. So I need a nice diagram. And I need to know the concentration of that formate. I need to know the initial concentration of the formic acid, the initial concentration of the hydroxide. So if you remember from the previous stoichiometry, I had 2.5 times 10 to the minus 3 whole weight. That's the number of moles. For ice diagram, as usually the case, I need the concentration, not the number of moles. Oh, fine. So what is the concentration? If that's the number of moles, what is the concentration and how do I find it? That's divided by 50 milliliters, which has to be liters. So that's divided by 0.05. Five times 10 to the minus 5? I'm doing this in my head, to be honest. I'm going to do this. No. 2.5 times 10 to the minus 3 divided by 0.05. What is it? 0.05, so it's 5 times 10 to the minus 2. So that's why I said I was doing this in my head. Okay. 0.05. Would you rather write it that way? So the initial concentration is 0.05 molar. 2.5 times 10 to the minus 3 moles, 0.05 liters, but it's 0.05 molar. So that's the concentration of that salt. That's the initial concentration of it. What's the initial concentration of my formic acid? Go all the way back to when we were working these kinds of problems. Initial concentration is always initial hydroxide concentration. Okay. Don't let that number up there try to pull into here. Those numbers up there, we've already used them. It's how we found this 0.05. We used all those numbers to get to this 0.05. Change. X, we're going to let that go down because it has to in order for these to go up. So at equilibrium, we have 0.05 minus X. And sure, let's check out our simplifying assumption. So I'm going to have X squared and 0.05. So now I need to clear this out. You got this? Erase this. So K is equal to X squared over 0.05. So we need to talk about this K. what K is this K? K, KB, yes. Because that equilibrium had hydroxide in it. That's my reminder. Oh, wait a minute. That equilibrium that we just did our ice diagram on is on a KB. So what is the KB for this system? Well, what's the KA? We've already been working with it. We used it in the Anderson-Ausubach equation, didn't we? What is it? 1.8 times 10 to the 10 to the minus 4. So what's the KB? Yep, 1 times 10 to the minus 14 divided by that 1.8 times 10 to the minus 4. That's going to turn out KB. So 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 4. 5.56. 5.6 times 10 to the minus 11. Is equal to x squared over 0.05. So x squared is that number times 0.05. 1.8 times 10 to the minus 4 right, so 2.78 times 10 to the minus 12. 2.78 times 10 to the minus 12. Take the square root of that. 1.7 times 10 to the minus 6. Alright, so 1.7 times 10 to the minus 6. I take the negative log of that. Negative 5.78. So my pH is 5.78. No. What is 5.78? My pH. Don't forget, again, this is another place where you're going to be here in the middle of all these calculations. You got this exam you're trying to finish, and all of a sudden you get 5.78. If you look, and sure enough, it's on the left. You think, all right, got that one, now move on. But wait, this is not pH, this is POH. Because X in my ice diagram was hydroxide concentration. Oh, boy. So the POH is 5.78, and finally the pH therefore must be 8.22. And again, we actually did that, except for the stoichiometry part, but once we got to our ice diagram, we did that in the previous chapter. It's been a while, I got you, it's been a while. We had spring break last week, and we had a week of lab, and then like a year ago, that we did those things. But we did those things. So refresh yourselves to make sure that you can go back and do those kind of calculations. After the equivalence point, we're just back to figuring out how much extra hydroxide there is. As soon as I know how much extra hydroxide there is, I'm right down the road. In fact, the pH of this is going to be the same as the pH of the strong acid, strong base. Go run the numbers. You'll see the numbers have to be the same. It's strictly on how much extra hydroxide there is. So, at the equivalence point, we did an ice diagram. We made all those things. And what you finally get is you get a titration curve. Okay? That looks like this. You got a buffer region, you've got an equivalence point, and then you've got an after the equivalence point. Initial, it's a weak acid, so it's got its ice diagram. Or you had that shortcut, right? Okay. Here you got a buffer region. All you need to know is how many moles of conjugate base, how many moles of acid. And then the equivalence point, now it's a salt. I don't got to know what the concentration of that salt is. I have on the KB. And then after, I'm right back to the same old ballgame. Okay. So, we're going to stop there, but essentially a weak acid with a strong base is the same kind of process